First of all, thanks Merantix for organizing. Thanks Merantix and SingleStore for organizing the event and having me talk over a very interesting topic. To start, I'll quickly start by introducing myself. Yep. So about me, I'm the co-founder and CTO at TopShelf, which is a startup based in Berlin. Um, my title says CTO, but I'm more the product guy. So, in case there are more technical questions you want to ask about RAG, you can ask Michael. Um, I'm going to look at RAG from more product perspective and a use case that we are using at TopShelf. Um, so uh, I've been in products since more than 8 years, and I'm more the product guy who can code. So I also have built apps from scratch in Flutter, and also I've done my share of implementing AI projects. Though majority of my experience is leading product and tech teams for startups and scale-ups. So let's start a bit. I know not everyone here is living under a rock, but let's start with what happened last year, right? End of 2022, OpenAI launched GPT 3.5. It was really revolutionary, and everyone wanted to implement Gen AI or do some sort of Gen AI startup. I would say TopShelf wasn't any different. We saw an opportunity, and more or less was the beginning of TopShelf. So uh, we did a lot of user research, and we found that especially in beauty and skincare industry, um, there are a ton of products. There are thousands of products. People are overwhelmed by fake marketing messages, and they don't know where to start when they want to buy a product that they're looking for. And that's where we thought we could come in. We wanted to bring honesty and relevance to product recommendations. And our key niche area we wanted to start was in beauty and skincare industry. And how we wanted to do was using two pillars. First, we wanted to start a sort of social network to sort of have our own proprietary data. So this social network, you can think of it as like Goodreads for beauty and skincare industry. So I'm someone who is using beauty and skincare products. Let's say I don't use that much, but um, um, I whatever products that I use, I can add it to my digital shelf. And then people similar to me and my friends can see which products the curated list of products that I use, and also um, uh, if there are any specific reviews, there are top products, flop products that I think are appropriate. Um, the second pillar of TopShelf is more where we are leveraging the search and the AI part. And we realized that just having a social network where you could see the products your profile similar to you're using wouldn't be enough, because still the number of products and the context was missing. And this is where the main application of RAG is. Let's take a simple use case. Lina wants to purchase a new cream for her as a solution for her pigmentation spots. She asks TopShelf chatbot, and she receives recommendation based on all the interactions she has had on our platform, and also based on the people she follows and who have similar problem with their skin. Now, to leverage this real-time context is where we are planning to leverage the power of RAG. But of course, there are some challenges. One option could be to fine tune the whole model, uh, but the data would be so huge that this would be very expensive. The, the main problem of LLMs, which you could have seen while using ChatGPT as well, is sometimes the data is outdated. That which means that LLM might recommend products based on outdated information. Maybe the product doesn't even exist anymore. Um, Another could be that we don't know what preferences does Lena have, and what are the interactions she has had, what products she has liked, what she has disliked. And last not but not the least, there are the problem of hallucinations. Not all product there might be solution for the product which is not necessarily what what she's looking for. And this is where RAG comes in. So think of it, I like to explain it in terms of a podcast. For example, we have um, a podcast host and a guest. Both of them have prepared the podcast. They have a set of questions, and the podcast is going on fine. But then in the middle of podcast, there is some context that is missing. They maybe it's like which who won the Euro Cup in 2022? And those who have seen Joe Rogan podcast or any podcast, this is a famous quote, like pull that up, Jamie. So you can pull the information live, right? This is somewhat what RAG is. Before I get into the details of uh, RAG, I wanted to sort of explain, mention where RAG lies in the spectrum of different methods of model optimization. Um, let's think of two dimensions. First dimension is context optimization, which is the y-axis here. And the second one is behavior optimization. Now, um, context optimization is really where mm, the more you go towards the context optimization direction, it's the live information, documents, or multimodal data that you need to improve the context of your output. And behavior optimization, which is along the x-axis, is the dimension which optimizes the output in terms of what tone do you want the output to be, or what, let's say, you want it to be more domain specific. In this regard, there are mainly three methods that come to mind. First is prompt engineering, which is really where most of the startups start implementing their LLMs. Fine tuning, which is, of course, you take a base model and then you train your whole data on top of the base model, which is, of course, it can be expensive. And the last but not the least is RAG. And this is a very special kind of technique which ensures that you retrieve the right data and context to be able to generate the right sort of response. When startups implement, it can start from basic prompt engineering, like I said, and a lot can be done with basic prompt engineering. So unless you really need real-time contextual data, prompt engineering can do a lot of job. But the path could be either any ways. You can start from prompt engineering, do fine tuning, do a bit of naive RAG, which is what we're going to talk about, and eventually there is also advanced and model RAG, which is more context based and an advanced phase. To get more specific with retrieval augmented generation, what is it? It's basically you prepare your contextual data, you chunk it and embed your knowledge ahead of time, perform search based on your need, and process and inject the context with the original query to the LLM. This is how it looks. It looks quite scary, but basically, in our case, we have the product catalog, the user data, and user reviews. This data is first goes to the initial chunking and splitting, which can be seen in the pre-processing pipeline. This is then further processed into embeddings and stored into the vector database. Through vector retrieval, this data can be retrieved with a contextual prompt. On the user side, Lena asks a simple question. This goes to TopShelf. The query is processed and is used to retrieve the right contextual data through the retrieval engine to the prompt. Further, the same query goes to the LLM, and both are combined to generate the right answer that is appropriate for Lena. Of course, there are multiple challenges that would be addressed by Michael. First of all, the handling of multimodal data sets with conventional databases can be hard. There is high computational resource requirement. Creating integration is not always simple. And furthermore, the usual data security and privacy issues. Last but not the least, reducing bias in retrieval is also something that needs to be looked into. How much time do I have? I mean, just to get into a bit of detail, I have broken down the whole chain in terms of what it means from a product perspective. The first phase would be ideation, which means identifying the use cases, validating with appropriate user research, check the requirements and the infrastructure, evaluate what chunking strategy would you be using, which embedding model would be appropriate, what vector database would be appropriate for you, and pre-evaluate your LLM tech stack, which could also mean which LLM model you want to use. Next step would be to build a basic prototype. Once you have established all your basics, you can build and test your UI and your data pipeline, retrieval pipeline, and the basic generation. Also set up evaluation methods that would help in the initial testing. Next would be to build a proof of concept based on, it is critical here to check with experts. It could be domain experts, it could be people, it could be your users if the output from your LLM is appropriate. Develop a detailed architecture for the operation, the final production. Optimize your retrieval and response quality, and ensure that the compliance and security mechanisms fit your need. Next step would be, of course, find the best practices that suit your requirement, which is more also determine the evaluation metrics, and it's more about preparing your product for launch. And last but not the least is deployment. This includes, then you could start optimizing the cost, see if the model that you use initially makes sense, and plan for the long-term application. Thanks for listening, everyone. Those who want to join the waitlist for TopShelf, please, the QR code on the right. And then those who want to connect with me on LinkedIn, the QR code on the left. Thank you.
Thank you very much. Coming to the next topic. We're going a bit, as we are here on the AI campus, I thought nobody's afraid of seeing a little code, so we'll dive a little deeper later on. But first and foremost, a little bit about SingleStore, because I was, for example, I was at a festival last week and was having a SingleStore shirt on, and somebody asked me if that's something like Tinder. And it is not. We are, but it's a fair question. I understand that. So we are a database or a data platform for that matter. So we started as an in-memory database a while ago and pivoted into a more generalistic relational database management system. So at the moment, we support different types of things, and we will focus today on vectors, semantic keyword search, and notebooks, for example. But there's a whole lot more in the platform. I will not dive into details around this, but the core of what SingleStore does is around real-time analytics. So if you have a data warehouse and you're doing your backend analytics there, that's all good and fine. But if you choose to do an end-user analytics dashboard where you have high concurrency, where you need sub-second queries, then SingleStore can come into play. Or if you want to store vectors, for example. To lean in, what we usually see with companies is a typical architecture of different data sources, databases, like the classical transactional or analytical databases, which you then augment at some point with some caching because stuff is slow. Then you add some search things like Elastic, for example. And now we are in the world of RAG, we're in the world of AI, as explained by Sushrut, and you add a vector database. What we essentially want to do is combine this ideally into one database to simplify the architecture, to avoid all the clunky ETL between the different systems, and to have everything in a very, very fast in-memory database, not only in memory, but a good chunk of it. Have it in a simple fashion, so you can interact with it using standard SQL or JSON adapters, and you can scale it horizontally to your needs, essentially. So this is what SingleStore does. Coming now to our little demo. So what we will do today, just have to make that a little smaller, there. What we'll do today, we had the topic today of multimodal RAG. So GPT 4.0 came out and did a pretty crazy job on doing multimodal tasks. So I will do a couple of more simple tasks here. But essentially, the stack we're using is we will use SingleStore, which you see here. So this is our cloud offering. We also have it as a self-managed variant, the software which you can just install essentially everywhere. We use it as a data platform for storing the vectors, for storing the embeddings. And we're using it also as a runtime engine. So you see here, this is the Jupyter Notebook place of the platform where we essentially interact with the data. As a LLM, we will not use OpenAI because everybody's using OpenAI, and I'm more a fan of Anthropic as a fancier name. So we are using our friend Claude here. And as a framework, kind of the glue behind it is LangChain in this case. But it's interchangeable, works the same way. If you want to use Llama Index, for example, to do it, it's just the same. For text and image embeddings, we're using the basic clip models. They are pretty small, very efficient, and run essentially in this notebook. So what we will do, I'll explain that as we go. Essentially, we are here connected to a database. This is my data workspace, and our database we're using is the multimodal one. And to start fresh, we first drop everything we have and then install a couple of dependencies. So this will take a couple of seconds till all this stuff is installed, and then do some additional stuff like telling the notebook where to store its data and getting our API key for Anthropic that we can interact with Anthropic here. Now, here is where LangChain comes into place the first time. So we're using here fast embeddings from Quadrant as a vehicle to get the embeddings or to host the embedding model, which is Clip. We are adding a vector store of type SingleStore. So SingleStore will be our vector database for the embeddings, but also for the text. And we're using here the vector index, which means essentially, you can think of it like if your vector data grows, you still want to have the queries return pretty fast. And that's where we're using vector indexes for. The vector index is kind of a bookmark concept. So it will live in memory and it will return in 10, 20, 50 milliseconds, depending on the size of the data and the size of the cluster you have. There are different variants of index types we support. I will not go into each and every detail around this, but the prominent ones, HNSW or IVFPQ, are supported by SingleStore. Then there are different algorithms to say, hey, how is this vector similar to another vector? We're using here in this demo .product, but there are also other functions to do that. And from a vector size, we're using here 512 dimensions. So this is essentially the length of the total vector. So see the embedding model essentially downloaded and the vector store is created. This would mean that now we should have a table again. And that table is called embeddings like before, like the one we dropped. And we will also see here some indexes. And there, the two ones that are here important is, like you saw before, with our vector index, that's here, that one. We see also the metric type there I mentioned earlier, .product. Could also be Euclidean distance or cosine similarity or whatever you want to do. And we have a full text index, which is kind of the same thing as you would use when using Elastic. It's just all living in SingleStore and it can work with any data type there. Another important thing just mentioning, because on the slide when I explained SingleStore, there was a topic called horizontal scalability. And to scale horizontally, we have to know how to distribute the data across the different nodes we have in our database. And this is controlled by our little friend, the shard key. And the shard key essentially says, hey, which element goes in which partition of the distributed database. All right. By the way, if you have any questions, if I should explain anything, don't be shy, just shout. All right, coming to the next one, here is the main logic of getting some images. And we are using here essentially a little CSV file. In that CSV file are a bunch of images. And we will download them, put them in a data frame, and essentially create down here. This is the important thing. The rest we can essentially gloss over. Here we will add the images after we created before the image embeddings and store them into our vector store, SingleStore. So this will now run for a bit, a couple of seconds. It will fetch the images from the different URLs, create the embeddings, and put those vectors into the database. Once it is done, and we can look that something ended up in the database, it will take a bit as it's still writing to the database, and then we will get a result now. And there you see how it's looking like. So there is, for example, a little text content. Text content is kind of the description of a image. And there is some metadata. The metadata contains the URL where the picture was downloaded. And then we have the vector embeddings. As I said before, this very long, 512 elements long to be exact, vector of which represent the picture. All right, now we can look which pictures have been put in the database and have been put into embeddings. And we can also look at a couple of the pictures. So here's one example of a library or something like that. And now essentially we can start interacting with the data. And as we have now pictures in the database and also have the text embeddings created before, the text embedding model created before, I can now essentially ask in natural language, hey, show me a couple of pictures or one image with a church. I put this query then in a similarity search with score. That's the function here. And K5 means give me the top 5 documents back. This will return essentially from all the pictures I put into embeddings, hey, which ones contain a church. We can now, as we don't believe the AI and what it does usually, can hallucinate. That's why we'll look at if that is correct, and looks almost correct. Like you could still say, okay, there's some Cook library, maybe you glossed over that one, but it looks awfully like a church, I would say. So I would say we can consider this task done right. And back here is the score. So this is kind of the similarity score. It is usually a number between 0 and 1. And it shows how similar to the prompt a certain image is. So there's a lot of other stuff on that image, so it will not be a 1, right? But the top results are essentially those 5 here. Now, if we go, yeah. Okay, it essentially takes this text, show me an image with a church, create a vector out of this question to have a semantic meaning of my question, and will query this, or we'll put this query into the database and say, hey, do you have any images that are similar to this? And will return me the top 5 results, and they are ordered by this score. So the highest score, the highest similarity will then show on top, which is in this. That's not necessarily the index, that's really the similarity score. The index is, again, something different. It's kind of related. So we can use, the index is used to speed things up. Because let's say if I have now I have like 20 pictures in, I can just do brute force and look over all of them. But if I have millions and millions of documents, that gets slow to read every line and to make that comparison and to get the exact nearest neighbor. That's what we say when we do brute force. But what we do when we're using the index, we're using the approximate nearest neighbor. So we're saying like, okay, you have a bookmark and do kind of a cube and say like, okay, what is the one that is approximately the nearest one? Yeah. Where? Yeah. All right, no worries. No, it does not come from Anthropic. That all, so now, till now, we did not leave this notebook. So we did not use any Anthropic OpenAI model whatsoever. We basically used a little clip image embedding model and created here the embedding. So this is the line that essentially before it iterates over each image and then creates with this image embedding model the numbers, the vector. This is where it does it, like in this area. The RAG essentially will come next, right? So now you have a question, you ask the question, and you get the 5 most similar results. And this you get now to the large language model to do things with it. No. There's no fine-tuning involved. We'll keep fine-tuning and pre-training for for a next session. That's like a little teaser. Yeah. Yes. Yes. In this case, yes, because let's say those models will create not 100%, maybe not 100% the let's say the same vectors each time to the last digit, but more or less those models they are like, I don't know, 200 or 300 max big, and it will be fine, right? So just to say image similarity, but let's say if you do it at large scale, if you have a use case where you have images of a certain type, then it may be interesting to do fine tuning and to adjust the model and also the embedding model to it.
Gave us the SingleStore index with full text search.
Yes.
Was the text index used here as well?
No, that was the next one. Then the questions came in. That was the next one I wanted to use. But yeah, first the questions. Yeah. This one, it is also vectorized, and then the text vector is compared against the image vectors essentially. So it's also vectorized, and then using the vector index or the vector search there. No, no. Exactly. Yeah. Yeah. All right. Many questions. Okay. Exactly. No, that's not what it does. At this exact query, it really does simply, hey, I create a vector for this question, and I have vectors for all the images. Give me a match. This is all what it does at the moment. Depends on the embedding model. So both are clip models, but the one is a vision model and the other is a text model. So the model to translate the query is the clip text, and the one I used for the images is the clip vision. That's the only difference here. Yeah. Yeah. Results are good. Yeah. That was just for demonstration purposes, but I think we'll come to that later on. Yeah. Sure. Better? Yeah. 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 No. I'll store the base image basically in a blob in the database, and the vector is a different field. Because I would always recommend to do this, because at some point in time you might change the embedding model you're using, and then you have to have let's say the base image still there to recreate everything, the vectors. Yeah. I don't know. But we can simply no. In this case, that did not work well. Like, this small embedding model will likely not catch the whole context of the question there, right? But yeah, again, we are, let's say, basically rapidly prototyping here in a very small notebook. But this could be adjusted. I could also have, let's say, in LangChain, I have also the ability to do filtering or to include negative values still within the query. I can do that as well, but I have not prepared that one. All right, I'll continue a little bit, because now to your question before regarding the full text index. So this query is now a little bit more complex, and it takes basically a similarity search with score. We know that from before. But now it has a search strategy attached to it, and this is weighted sum, which essentially means, hey, I have a vector index, but I also have a full text index, full text search index. I can now weigh them, and the one goes essentially over the image description, and the other one goes over the image, which means if I put now the text weight to 1 and the vector weight to 0, I get results that are containing a library, right? What you would expect from a full text search, right? So description has that. But if I do it the other way around, then we have some interesting result here, because let's say we still have here library in, here library in as well. But here, for example, in this interior of hotspot, and I think that is the image from before, this still shows up at number 4. And this now shows pretty much the difference here. So this room, this was the initial image. It does not have library in the description, but it looks like a library room. So this what you can think of now as a vector search gave me that image back, because it said, okay, it looks like it, so give you the result.
But, I mean, it does say reading the description.
Yes. Yes, but a full text search does not care. Exactly. It will, let's say you can adjust it so you can do a fuzzy match and stuff, but it's still, if it's not like 1 character away or 2 characters away from library, it will not care. No. The description of the image is purely full text search. So what you know from your Lucene, Elastic, or other stacks. All right. Now we come to the part where we actually include the large language model. And this is essentially done here, and I'll let that run quickly. It does not output anything yet. Just to give you a bit of an idea, it has a couple of functions in here to essentially take the image, put it into a machine understandable format, so base 64 representation of the image. Takes also the context of the description and the image URL and gives all that context. And now we are really in the rack type of situation. Gives all that context to Claude. And we are using now here the small Claude model from Anthropic with the temperature set to 0. So I don't want the model here to make things up or to be very, let's say, creative in its answers. I just want give me the answer that I have in my knowledge base or in my image set. Now, here we have again now a query. Query is give me a picture with an ice bear, and I run again the query we know from before. Give me the top 2 elements and run this, see, okay, I have a result from my images. There is an upright polar bear in Cincinnati, blah, blah, blah. And now I'm giving all that information, doing the RAG case, give it to Claude and let it explain. And now we see what a large language model does with it. And it gives me a bit more context because it takes the full image. And in this case, it says, I apologize, but the image does not provide a bear. And if we look at the image now, just copy the number, where is it? So this image is, it looks like a polar bear, So the simple result will be fine, but the large language model will see that this is a statue of a polar bear. It's not a real one. And it will give me that information. And this is essentially then how I can give a question and an image context to a large language model and do stuff with it, like in this case, interpret a picture. Right. This was a brief overview of that. Yeah. That definitely is a polar bear, but just a statue. So Claude was actually quite descriptive in understanding it. It says likely a library or a museum. It's a statue. It's not a real one. Don't be afraid of it. All right. And this essentially we can do with different things, and we don't even have to use Claude like an external large language model with it, because what we can do here as well, but this is kind of stuff I parked for the next iteration of this. These notebooks can run in different flavors, and here now I use just a small one. I have just these small embedding models. They can run essentially everywhere. They're not very big, but we also have a big machine which has some GPUs. So what we can do here as well in SingleStore, run, for example, a fine-tuning or a pre-training of an existing smaller module that fits into this category of machine, and train it or fine-tune it in the platform as well. Because this is also what I want to leave you with. What we had today is essentially looking at RAG. And we saw in the slide before, there are other techniques like fine-tuning and retraining of a model. And even though, let's say, if you store embeddings and get big context out of a database like SingleStore, that would be good for us. But it's really not very smart to do this or to do it just like this, because I know these large language models, they have big context windows and you can just feed them tons of data, but it will be very expensive very soon. So what I would always recommend is look at your data, look at the different texts, images, voice stuff you have, and think about what is changing a lot, what is not changing, what is static content, what is used then for example, fine-tuning or retraining a model to let it understand what I'm doing or the core language of what I'm doing, and only use RAG for high-velocity data where you need in-context learning of or in-context generation of answers. So this is kind of my recommendation in all of this, because you have a whole lot of open source tools out there to do just that, and you don't have to use the context windows for each and every request to its fullest extent. And I think with that, I would open for questions if there still are some questions. If not, you can also approach me afterwards. Yeah. Yeah, so the question was, if I have a humongous database with different relations, relational database, yeah, can I tell or can I let a large language model learn that? And yes, and fortunately, I have like a spare thing here. This is kind of a little UI, and this is also running on SingleStore, and it was essentially trained with the structure of a database and the or different columns and different dependencies with each other. So in this case, it's like, I think it's a marketing tech application or data set there. and it is trained with that. So this is what I'm using for RAG here. And essentially what I can then do is I can, and I make this a bit bigger again, I can now talk to the database in natural language. So for example, it gives me some recommendations of what has been asked before. And I can just ask in natural language, and what the model here will do is translate this into a query and run it on the data. And you can't see anything here because it's not the right color. Yeah, you could do that in natural language. You can talk to the database, and then you can also give feedback. So for example, if it returned with a result, so in this case, the result is fine, just the line is the same color as the background. So it's not very good for you right now to see that. But anyways, it's the right answer and it's the right query that returned. And I can now, for example, if I put yes, this will go to the knowledge base and it will be used in future RAG scenarios and give me recommendations for this. And now also follow-up questions. And this is how I can consecutively train use my large language model to help me talk to my database if I don't want to write queries anymore. Yes, that's doable. Yeah. There are a couple of, let's say here, it's all around of what quality is the training data and what is the model you're using. Again, here I'm using Claude, and this is likely not the best model to translate text to a SQL query. It does a good job, but there are better models. For example, Snowflake has a model for that. I'm using it for the training embeddings to understand the information schema of the database. But I would be very conscious of choosing the right model and then also maybe fine tune or pre-train it on my specific schema. If I have, let's say, a schema or a part of the schema that's not really changing, then I would think about fine tuning for a certain amount of or for a certain structure of the database, and then only use the RAG piece for the more frequently changing stuff. That was a question.
Yeah, so back to the images and text before. How do you see the importance of the vector lookups, or also for text-based RAG? Like, how do you see the importance of the vector similarity versus search for typical applications like whatever, asking questions on a document database or documentation or contracts?
Again, unfortunately, it depends. If it's let's say financial or legal language, for example, then I would be I would take that into account when, for example, looking for the embedding model. There is a company called Voyage. Voyage has just brought out a couple of new embedding models specifically for financial dealings and for legal language, because this could be very, very specific, right? So this is kind of where I would start, and also in the model that is then used for doing RAG, I would try to use a specialized model because likely the quality is better, or even fine tune it a little bit to my understanding. And I left out, so we are talking English here right now, I left out the whole language piece. The big models are very good in talking different languages, that's all good and fine. But I had a customer recently from Slovakia where it's thin. There are a couple of special models, but then you have to really look for one of those to do the job best. Yeah. And now, to answer your actual question, if it's just for, let's say, text search, does not catch the meaning, right? The semantics. So if you have use cases where you could express like library, something in different words, it's a book room, it's a reading room, it's something like that. This is where text search hits its limits and where you are better off using a vector similarity search.
When does it text differ?
Like text is when they, it depends a little bit, I would say. I would always use a combination, and I would try to, like we did it before, maybe pre-filter with a full text search if I have a good quality, and then do the actual similarity with a vector search. That way I get best of both worlds, because it's also around, okay, how fast do queries return? How many lines do I have in the database? So speed and cost obviously is always a factor in as well. And let's say full text search from a speed and cost perspective depends a little bit, but could also be higher than even storing it in vectors, right? So it's hard to give you a one shot answer there. So it really depends. Yeah. Yeah, you could, but then you have like the latency back and forth from the LLM and then the search. This is kind of the question is always like how relevant is speed and how many round trips, for example, to an LLM can I do? And I would always try to filter to a small context, as smallest context as possible before, and then send it to the LLM, because you will have the advantage of speed and also of cost, because the less tokens you send, less bucks you pay. Exactly. All right. Ben? Yeah. So you have here the concept is like we have let's take here. So here in this case, again, as I said, this is the cloud variant of it. There's also a self-managed variant where you can just install it. We have a workspace concept. Workspaces are essentially the compute, and the storage, like the databases, are detached from it. So you have storage on the one hand, compute on the other hand. And the compute is hosted in AWS, Azure, or GCP. And you can choose where to put it, and you can choose in which region, and you can choose the size. So in this case, it's the smallest cluster we have. And there you could then, depending on your workload and requirements, you could also say, okay, I need to resize it because I have a lot of big event coming. We've also, let's say, included auto scaling here, so you could also let the platform do it themselves. But essentially, there you can then size your compute to fit the concurrency, the query speeds you're looking at. And right-hand side, you see the databases that are attached to it. And we were working at this database today, and also at these two. These two were the text-based interaction with the database. The one had the training data, and the other one had the actual data, which we were querying. Yeah. Yeah, and notebooks sit on top of it, and then you can write Python, SQL code, and interact directly with the database.
You mentioned the cost between LLMs and data, and they will scale exponentially or expensive. Do you have any indication like we have the total cost from Azure, they're moving the GPU based.
Yeah.
Do you know what will happen in the future?
I have a feeling. No, honestly, my perspective is like if you take RAG to the extreme and take the LLMs to the extreme, they will be paid based on how much you use their service. The more tokens you put in and you get out, the more you pay. So an LLM provider will always like be very interested in getting as much data in and like, don't bother pre-filtering, send us everything, we'll figure it out. This would be my perspective if I were an LLM provider. And this is the feeling I have, the direction in which it goes. My personal opinion, and also let's say I looked at the recent Apple announcement, having more specialized and on-device models that do a certain task pretty good, and only, let's say, go to the big providers if you have a task that can't be done by a small self-hosted special ones where you don't have to care about privacy and stuff because it sits in your premises. Do it like that. I think that will, in the long run, be the more cost efficient. And also given the speed of innovation at the moment, like every week, if you watch Hugging Face, every week there are new models coming out and beating again the benchmark, which is bullshit because everybody trains on the benchmark. And so it's such a fast moving space that I would, even when I would use an LLM, I would like, or I would recommend to keep the access to the LLM as flexible as possible. So use, for example, Llama Index, LangChain to be able to just switch the models as you go. Yeah. 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 Once they are vectors, they are kind of more to the machine. So the machine understands it, and the language piece is more or less evened out. So as long as, let's say, if you do text and image, you have to think about that the text and image models, the text and image embedding models work good with each other. That's why I used clip vision and clip text for both. When it comes to language, once they are vectors, it doesn't really matter. But now, if we're asking a German question to that clip model, this is trained specifically on English language, and it's not many tokens on how this has been trained, because it's like, again, 200 or 300 meg. So this will not fly. If that's your use case, yeah, or use one of the multi-language models that yeah, if we are talking embeddings, I would always recommend going to Hugging Face, to the massive text embedding leaderboard, and there you have, for example, also the language piece where you can say, okay, for specific tasks like retrieval, so to create embeddings now, which would be the best scoring embedding model for this one? And then you can pick and choose, because let's say they always also differ on, say, the size. So these are quite big models. So there you need some hardware to run them. And there are also, let's say, different other types like law, for example, or long embed is if you plan to embed really long texts, because this has to be done differently than just a sentence, for example. All right. Then I would say I'll leave you to pizza and beer. And thanks for all the questions to make it interactive. Thank you very much. See you next time.